Hello folks! Okay, last time we talked about automation in general. This time we're going to create a simple bash script to try and do some automated testing for us. So we're going to do this very incrementally. We'll just start with a couple of really simple commands and we'll just expand and expand and expand until we get what we want. Now I want to keep this something that's reasonable for a short run through like this, so we're going to make a few simplifying assumptions for our script. The program under test is going to take its input from standard input, it's going to write its output to standard output, and it's not going to take any command line arguments, it's not going to do any file I/O. So nice simple program in terms of input and output. It's supposed to exit with an exit status of 0 if everything went well. Anything else means it's an error. And for every test case, we're going to use a file to hold the input to use, right, that will redirect to the program under test. And we'll have another file that contains the output we were expecting. So that's basically the ground rules for what we're assuming when we're automating. And what we'll do is we'll just have a bunch of the information that we're going to use stored in variables in our script. So we'll have one variable that's got the name of the program we're testing, one variable that's got the name of the file that holds the expected output, one variable that's got the name of the file that contains our test case data, the data that is what the user would be typing in. We'll have a file that we'll use to store the actual output, and maybe we'll store the differences between the expected and the actual output in another file. So we'll use O file for the actual output and D file for the differences between what we got and what we expected, if any. So the simplest approach that we could do to run a test case and capture the results would simply be to say, okay, I want to run the program taking the input from this file, from our test data file, and sticking the output in our output file. And then we'll capture the status, right, which is in that $? Variable. And there, we've run the program on the test data, captured the output, and we've got the status. So simple start. We could do this and then sort of manually look at it and see if it looks like what we expected, or manually do a diff between the O file and the E file to see if they match or not. But we've got a starting point at least. Now, maybe we look at that and go, well, gee, what happens if the program produces tons and tons of output? You know, it gets stuck in an infinite loop spewing out output, or it just spews out way, way, way more than we're expecting. Then when I go through and redirect this stuff to a file, it's going to suck up all my disk space and I'm going to run into some problems. So maybe as a safety valve, what I'm going to say is, okay, let's run the program, but instead of just putting all of the output directly into a file, I'll stick it through something first that cuts it off if it gets too big. So one of the things we can use is that head command where you can specify some number of characters. So we'll use head-c and the number of characters we want and say, okay, keep this many, throw away anything else. So now what we're going to do is run our program from the input data, run it through head, and we'll have another variable, climit, that's just got our upper bound on how many characters we're willing to keep. So, you know, maybe I say, okay, well, the program should only be spewing out 100 characters or something like that. I'll set climit to 1,000 just in case. And we'll say, okay, now run the program, stick the results into head so it only keeps the first however many bytes. And then once we've done that, put that into the output file. That way I know I'm not going to go crazy and suck up all my disk space on a broken program. So that's not a bad idea, right? And again, it's nice and simple. But one of the problems is that when we do this, when we pipe the output through head, all of a sudden we've lost access to the exit status of our program. So because if we try and capture the exit status after this, we're going to get the one from head instead. So maybe we decide, okay, well, you know, I'm not that brutally concerned about efficiency. Maybe I just run it twice. Maybe I run the program once to capture the return at the exit status, and I run it once to capture the output in the output file. So what I'm going to do is basically throw away the output from my first run. Now, there is a file, sort of a file, called /dev/null. And this is, if you like, the dumping ground for anything you don't want to keep, any output you don't want to keep in running your Linux programs. So if you direct your output to /dev/null, it's basically sending it off into a black hole and it's never going to be seen again. The information doesn't actually wind up getting stored. So I'm going to do that. I'm going to run my program and just say dump the output into /dev/null so it disappears forever, but I'll capture the exit status. So now I've got my exit status and stored it in a variable, and now I can do my run where I go through and run the program, on the test data, keep just the, first however many bytes if it goes too long, and store that in my output file. So now I've safeguarded myself from runaway output in the program. So now let's do the same sort of idea and deal with, well, what if it just goes into an infinite loop and sucks up all, it sits there and runs for 2 days. So I'm going to stick a timer on it. Say, okay, well, after a certain amount of CPU time, cut the program off. So there's another program called ulimit that basically says, okay, limit the CPU utilization to whatever I specify next. And so we can come up with some variable, I'm going to call it CPU, and say this is the number of seconds of CPU time that I'm going to limit this thing to. If it goes over that, just kill it. So the way it works is you say ulimit -t and the time limit you want on it. You can specify limiting other things for it, but we're just focused on time here. And then you run the program, sending the results into dev null, and you do the same thing for your second run, where you're saying, okay, run the program, limit the CPU time, and put the results in climit. Now, one of our concerns here is the idea that the program could crash, right? It could be buggy, and based on this test file, it could crash, or this test input, it could crash. We don't want our test script to crash if the program crashes. So what I'm going to do is I'm going to run my program in a shell. So I'm going to run this. If you see the $ and the brackets around all this, if the program happens to crash in the midst of this, then my script doesn't crash. It's just the interior of that little shell that it's running crashes. And then I'll do the same thing on the second run, of course. Now, that also has the advantage that this ulimit, this time limit, only applies within this shell. If you do ulimit at the global level, then you could very well be turning off your ability to run programs that take more than that amount of CPU time in the future. So it's not a bad idea to stick that in a shell, so you're limiting the environment that this is happening in. And so here, we're limiting the time that a program can take. We'll run this one in a shell where we run the program, pipe it through head, give that whole thing a time limit. And again, so now we've protected ourselves from output overruns and from CPU time overruns. For that matter, if the program just hangs, well, no, this won't catch if the program hangs because we're based on CPU time. Never mind. Ignore my babble. Now, we should probably test the exit status at some point and give the user an idea of whether or not the program crashed, whether or not it exited with an incorrect status, a non-zero status. All right, so after we do that first run, where we threw the output into dev null and we captured the status, we'll just do a check. Okay, is the status not zero? If it's non-zero, something went wrong. So we'll print a failure message. That test case failed. Right, so we're printing the name of the file and telling the user that, or the tester that, okay, it failed that particular case. So that's nice and straightforward. If we want to test the output to see if the output matches what we were expecting, well, diff is a nice straightforward program that just does an exact line-by-line comparison of two files. So if you do diff file1, file2, it'll tell you that these two files differ in these lines. And if you're ever looking at if we go back to our playing with Git, right? Git often does diffs for us to show us the difference between a new version of a file and a previous version. So the syntax won't look that particularly unfamiliar if you start playing with diff. Now, we've done our instruction to run the program time limited, capture the output, store it in an output file, and we've got that expected output file. So we'll just do a diff on our output file with the expected file, and we'll redirect everything that comes out of diff, so the standard output and the error output, and we'll stick it in our file of differences. So now we've got a file that shows us what's different between the two. So we can look in that and see what's different, or we could look in that and see if it's empty and say, oh, well, it's empty, everything must be okay. We can actually take advantage of diff in another way. It actually returns an exit status of 0 if the two files were the same, and it returns a non-zero result if the two files were different. So if I do a diff and it gives an exit status that's non-zero, then I can simply say, they were different. Test case failed. I can take it one step further than that. And what we can do is use a little blurb of bash here that basically says, if this command succeeds, if it runs with an exit status of 0, then run this other command. If it doesn't succeed, if it exits with a non-zero status, run some completely different command. So this is the kind of syntax that we can use. Run command 1, and if it succeeds, run command 2. So what the AND is doing is basically saying, okay, if this one succeeds and this one succeeds, you're done. And we'll throw in this OR here that's saying, okay, if either of those two fail, run this one. So what I'm going to do is say command 1 is going to be my diff. So if diff succeeds, run command 2, which is just going to be an echo statement saying it succeeded. Now the echo is never going to fail. So the only way this pair of commands is going to fail is if the diff fails, if the diff finds a difference between the two files. So my alternative is going to be to say test case failed. Something's different between the two files. So this is the idea we're going for, and here is the command. Again, the command looks uglier. This is the basic thought that's going on. We're saying do a diff, store the results in this diff file, and if that succeeds, print this message that the test case passed. Right, so that's my first pair of commands, and you see we've got the diff in one shell there. We've got our echo in another. If those both succeed, then we're done. If either of those fail, then it's going to go on and do the OR part and run that the test case failed. So with that little trick and diff, we can go through and insert an instruction that says, okay, compare the two of them. If they're the same, print that it passed. If they're different, print that it failed. So all sorts of fun and wonderful things you can do with bash. It's just knowing how to use this stuff. Now, all of that was for a single test case. Right? Generally speaking, we've been talking about the idea that we want to be able to run a whole slew of test cases. So what I'm going to assume is that we've got a couple of different directories. I'm going to have one directory that's got all of the files to be used as input. I'm going to have another directory that's got all of the files to show what the expected output would be. And then we'll have a third directory for storing the actual output, the results for these. And so what we'll do is assume that the file name is the same for all three. So let's say I've got a test case T1, then there'll be an input file called T1, an output or an expected output file called T1, and an actual output file called T1, each in different directories. And so what I'll do is when I want to run the test case, I'll run it on the T1 from the input directory. I'll compare it to the T1 in the expected output directory, and I'll actually store the results in a T1 in the actual output directory. So I've got these 3 different directories, and they'll all have a bunch of files with the same name. And again, I'm going to assume that we're going to use variable names to hold, or variables to hold the names of the input directory, the expected output directory, and the actual output directory. And so if I was setting up my test, or getting my script ready to run these things, I would simply go through and create those set of directories, create my variables for them, and we'll come back and have a look at that in just a second. And now what we'll do is say, well, I want to go through and for every test case in the expected, or in the input file directory, grab that file, figure out what the names of the other 2 files would be, go off and grab them, and run the test case. So for each file, for each test file in the input directory, right? So we're saying for everything that's in that input directory, we'll get the file name. So just grab the file name off the end of this. So you've got your path and then the file name at the end. Base name lets us grab just the file name part. Then we'll generate the names of the other 2 files. So eFile will be whatever the name of the expected output directory is, and then whatever the name of the file is. And then the actual output file will be whatever the results directory is and whatever the file name is. Right? So I generate the names. I've got the name for my test input file. I've generated a name for my expected output file. I've generated a name for my actual output file. And my loop is basically just going to say for every one of those test files, do this. Once you've got those 3 names, then do that test case. So all of the stuff, all of the code that we've created previously would be sitting right here. Saying, okay, I've got my assorted file names, run that blob of code. So again, the structure isn't that complicated as long as we take it one step at a time. Now, one of the things I wanted to mention is that you can create temporary files. Files that only exist until the script ends and then are automatically deleted. This way you don't have to worry about manually deleting them. Ooh, there's a typo there. mktemp should have an E in it. So if I want to generate a new file that's only going to exist until this script ends, you can use mktemp. So that file, the D file that I was going to use to hold the differences between the expected output and the actual output, I'll just name that file. I'll use a temporary file for that. So my D file will be my mktemp. So if we're looking back at this, we've got names for the test input file, for the expected output, for the actual output, and for the differences between the 2 of them. And then that blob of code that we created earlier to actually run that individual test case using those file names. So this is obviously horribly ugly. Let me zoom in here a little bit and see if we can get something that reads a little bit clearer. So this is just that whole thing put together. We've got our bash script. We've got variables to hold the names of the program that we're testing, the directory that's got all the input files, the directory that's got all the expected output, or expected output files. We've got the directory that's going to hold the actual results. We've got variables for the limit on CPU time in seconds and the limit on the number of characters of output that we're willing to store. And then we've got this loop that says, okay, for each file in that directory of file input files, grab just the file name from it, create the name of the expected output file, with that from that expected output directory, create the name of the actual output where we'll store the results, create a temporary file to hold the differences, create a variable to hold the exit status from the program. I'm just going to initialize it to 0 here. Run our command to capture, essentially just to run it and capture the return value, and again dumping the output into the black hole. Check if that came out with a non-zero exit status, in which case print an error message. Otherwise, run the command to dump the output into our output file, again limiting the number of characters of output that it stores and limiting the CPU time that it can use. Do the diff on the actual output and the expected output, and if that succeeded, print file passed. And if that failed, then print file failed, or print test case failed. And there we've got it. Right? So we can put together a script that will go through and do all of this for us. Right? We've got a functional bash script. Yeah. Now, I did want to say a couple of things about the way we've captured the output here. So in that particular case, I assumed that output only went to standard out. It's pretty likely that a program's going to have some stuff going to standard error as well as some stuff going to standard out. That introduces some complications because it means that we do have to capture both streams when we're going through and doing our testing and analyzing it. But it also means that we need to test that the sequence of stuff going to standard error and stuff going to standard out is correct. So if we expected the program to print, this to standard out, and then this to standard error, and then this to standard out, we need to make sure that's correct. But we also need to make sure that the right things go to standard error and the right things go to standard out. So this might mean doing two separate runs. One where we send both standard out and standard error to the same destination. So using the 2 greater than and 1 to interleave the two streams and send that to head and send that into a file. So that would be sort of the way the user would see it if they were running it interactively, right? So that's got all of the output from both appearing on the screen in the correct sequence. But that doesn't, we can't look at that, and because they're interleaved, we can't see which ones are going to standard error and which ones are going to standard out. So we might want a second run that separates the two of them, sends the standard error to one file and the standard output to another file. And that would also mean that we need 3 expected output files. One for just the standard output, one for just the standard error, and one for the combination of the two. So we would have to go back and tweak this mess so that in here we actually did a couple of separate runs. We did one run with the two of them interleaved. We did one run with the two of them split into 2 different files. And we'd actually have 3 diffs. We'd have a diff for the interleaved version, we'd have a diff for just the expected output, and we'd have, or for just the standard output, and we'd have a diff for the standard error. So that is probably the most basic tweak we would want to add. There are lots of things that we'll consider adding in the future where we start thinking about, again, command line arguments, and what if there's file I/O, and what if there are side effects to check, things like permission settings and whatnot. What if there are scripts that have to be run before we test the program to set the proper file permissions ahead of time, or to set up the right files in the right places ahead of time. So there are lots of additional considerations to play with, but we'll save those for another day. All right, we'll leave it there.